We're going to continue talking about gases today. Last time we talked about the property of gases, and we also introduced 4 variables. One of the variables was pressure. What are some of the other variables we mentioned? Temperature. Moles and?
The stretchy bounce.
Volume. The stretchy bounce describe the elastic nature, and that's just a property. But the variables we're looking at are volume, temperature, pressure, and moles. And we're going to talk about 3 of those today as we introduce gas laws. We'll get into more gas laws next week. And then later on we'll apply stoichiometry to gas laws, and we'll do 2 really cool labs. One next week and one the week after. The gas chapter takes quite a while. There's quite a bit of content to cover. We're going to pick up with the gas laws today. This is really, really easy. First hour found it to be very, very easy. The only thing I will say is you must get into the habit of identifying your variables, labeling things clearly, and setting up your expressions. And I'll show you a somewhat new way to do math today. I think most of you will buy in. The first gas law we're going to talk about is Boyle's law, and Boyle's law shows that pressure and volume are inversely or indirectly related when temperature is held constant. So if the temperature is at 30 degrees Celsius and it doesn't change, if you apply pressure, increase the pressure, you'll see that the volume decreases. If you decrease the pressure, you'll see that volume increases. Boyle studied this relationship between volume and pressure, and you can see this graphically in the following way. This simulation shows as you increase pressure pushing down on the piston, the volume decreases. You can see it graphically here. As pressure increases, the volume decreases. So that's an inverse relationship between pressure and volume. When 2 variables are inversely related, the way that you show that mathematically is that you multiply those 2 variables. So again, as you increase pressure, the volume is going to decrease. These 2 variables are inversely related. So as the pressure increases, the volume decreases. As the pressure decreases, the volume increases. And again, we can show this inverse relationship by multiplying pressure and volume. They will be equal to some constant K. We can have 2 sets of conditions. We can have pressure and volume under one set of conditions and pressure and volume under a second set of conditions. And if they're both equal to constant K, we can essentially get rid of this middleman and just have a formula in which P1V1 is equal to P2V2. And we can use this formula and solve for one of the missing variables. Graphically, I showed you. Let's take a look at the following example. There are a number of different ways to solve these types of problems. Some of them really can be solved in your head. Others will require that you write everything out. In the first example, it says helium occupies 4 liters of space, volume, and exerts a pressure of 2 atmospheres. The pressure is going to be increased to 6 atmospheres, and we want to know the volume when the temperature is constant throughout. There are a number of different ways to do this problem. Those of you who really like to do mental math, you're going to drive it this way. What happens to the pressure as it goes from 2 to 6 atmospheres? It increases by a factor of 3. So if pressure increases by a factor of 3, volume must decrease by a factor of 3. And 1/3 of 4 would be 1.33 liters. So some of you will see it right from the information provided and knowing that pressure and volume are inversely related. Some of you will need to write everything out. I just wanted you to first see that relationship, because in a multiple choice type question, it may say something to the effect that if the pressure is tripled, what happens to the volume? Decreases by a factor of 3. if you were to write all of this information out, under the first set of conditions, which I'll call V1, the volume is 4 liters, and under the first set of conditions, which is P1, the pressure is 2 atmospheres. If the pressure, P2, is increased to 6 atmospheres, now we're under the second set of conditions, we want to know V2. We have P1 V1 is equal to P2 V2. Don't plug in quantities right away. It is much easier to manipulate variables. If I want to solve for V2, I will divide both sides by P2. And now V2 is equal to P1 V1 over P2. And then you can plug and solve. And again, no numbers for chemistry. We have quantities. You have 2 atmospheres times a volume of 4 liters over 6 atmospheres. And again, atmospheres will cancel. 1/3 of 4 is 1.33 liters. That's the volume under the second set of conditions. Make sure your answer makes sense. We increased pressure by a factor of 3. Volume must decrease by the same factor. Pressure and volume are inversely related according to Boyle's law. I think this is one of the easiest gas laws, yet it's the one the kids confuse the most.
So could you not just divide by 3 after you see that it's a 3 times increase?
Yeah, sometimes it is as simple as that, and yes, you can. The second problem is equally as simple. I just want to make sure that you can pull the variables out. It says the air in bubble wrap exerts a pressure of 0.500 atmospheres when the volume is 2 mils. If the volume's decreased to 0.250 mils, what pressure will the air exert? Temperature is constant throughout. So what does the 0.5 atmospheres represent? P1, pressure under the first set of conditions. What does the 2 mils represent? Volume. And if you don't want to label as you go, in your problem, you could really insert right above here as you were working it. You could say, oh, that's P1. You know, you could label as you go if you don't want to write every little piece out. Or alternatively, you can write it out. Now the volume, second set of conditions, is decreased to 0.250 mils. So decreasing by a factor of 8, we want to know the pressure under the second set of conditions. So again, volume's decreasing. Some of you may not see the factor of 8. Solve for P2. Give it a shot. Start with your formula. Actually, we can do this one together. If you're solving for P2, what do you divide both sides by? And again, it is so much easier to solve by manipulating variables. So now P2 is equal to P1 V1 over V2, and you essentially have 1/2 times 2 is 1, 1 over a quarter is 4 atmospheres. And again, the volume decreased by a factor of 8. You would expect the pressure to increase by that same factor. Boyle's law. The indirect relationship between pressure and volume. Easy peasy?
Yes.
Alrighty. We want lots of those on the quiz. Yes, yes?
Yes.
Alrighty. The next two gas laws that we are going to talk about show direct relationships. Be very, very careful in this chapter. Whenever dealing with temperature, you must be in Kelvin, or you will crash and burn. Careful, careful. The next gas law we want to mention is Charles' law. Charles' law shows the direct relationship between volume and Kelvin temperature. Jacques Charles showed that when you heat a gas, it expands, and when you cool it, it contracts. So as you increase temperature, volume increases, keeping pressure constant. If you cool it, the volume decreases. And this is exactly what we're going to be doing in the lab. We're going to heat the gas, and then we're going to cool it quickly, and you will see that the volume of the gas decreases with the decrease in temperature. Now, when you want to convert from degrees Celsius to Kelvin, as we mentioned the other day, you simply add 273.15. So volume and temperature are directly related. When you want to show a direct relationship, you divide the variable, set equal to some constant, expand upon it for two sets of conditions, and Charles' law is right here. V1 over T1 is equal to V2 over T2. If you consider this graphically, volume versus temperature, as you increase temperature, volume increases as well. And you'll be generating such a graph in the lab. Another way to test this is to have a balloon that's inflated at room temperature. Put it on a bath of liquid nitrogen, which is very cold, and you will see that the volume of the balloon decreases with the decrease in temperature. Directly related to Kelvin temperature, not degrees Celsius. So you must do these problems in Kelvin, even if they ask for degrees Celsius. This is the one mistake that one kid very often makes from each class. Be careful. Don't be the one. You can't pass the quiz if you do it in degrees Celsius. Kelvin, Kelvin, Kelvin. We'll explore atmospheric pressure a little bit later on when we talk about boiling point elevation. I'm not concerned with it here. First example says that krypton occupies 4 mils of space at 10 degrees Celsius. What have we identified? V1 and T1. But can temperature be in degrees Celsius? No, 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 no. If the temperature is increased to 50 degrees Celsius, what volume will krypton occupy if the pressure remains constant? Let's take a look. So this is going to be Charles' law. In the first example, we have V1 is equal to 4 mils. T1, we were given 10 degrees Celsius, to which we had 273.15, so we have 283.15 Kelvin. No degrees for Kelvin, just capital K for Kelvin. Now the temperature is increased to 50 degrees Celsius, which is 323.15 Kelvin, and we want to know the volume that the gas will occupy. Pressure is constant. My formula is V1 over T1 is equal to V2 over T2. I'm solving for T2, so I need to multiply both sides by what? T2? And again, variable manipulation, critically important in all of the physical sciences. T2 is 323.15 Kelvin. V1 is 4 mils. T1 is 283.15 Kelvin. Again, those units will cancel. You're left in a unit of mils, which is a unit of volume, and there's your volume. After I do all the calculations, I really like to make sure that my answer makes sense. The temperature increased, so I would predict the volume would increase as well. And it did, which is a good sign that I've set it up correctly. Question?
Yeah. How do you know how many sig figs you have?
In terms of sig figs, I usually just go back to what I was given, and the smallest number given was 3 sig figs, so I'm giving back 3. And I usually do work in 3. On this classwork, though, you'll see I tried to make sure you really paid attention to sig figs. Sometimes I have 1, 2, or 3, but on the quiz, I'm usually in 3. The second problem is a little bit different, and I just want to show you a very cool trick that should allow you to solve problems more easily. The second problem says that chlorine gas occupies 5 liters of space at 200 degrees Celsius. I have my first set of conditions. Then the volume is decreased to 1.5 liters, and I want to know the temperature. If the volume is decreased, what must the temperature do according to Charles' law? Decrease, because they are directly related. So I'm going to pull my variables out, and I know some of you are just swimming ahead because you get things right away. I would like you to take a look-see at this for a minute. V1 is 5 liters, and T1 is 473.15 Kelvin. How did I get that? I added 273 to the 200. My second volume is 1.5 liters, so the volume decreased. What would you predict the temperature would do? Decrease as well. Now, our formula for Charles' law shows the direct relationship between volume and temperature. If you are ever solving for a variable in the denominator, be very careful. It's really important that you get it to the numerator, otherwise you might wind up solving for the reciprocal. If you get a minuscule temperature, you have solved for the reciprocal. Be careful there. There are a number of ways to get this to the numerator. In math, you probably would just cross multiply and solve. One really cute trick that works nicely and will serve you well here in math and SAT math as well is to do something called the double reciprocal. And essentially what that means is flip both fractions over. You cannot only flip one. And so when I write my formula, I don't even write this. I immediately write this. This is perfectly legitimate because 3 over 1 is equal to 3 over 1. Is 1/3 equal to 1/3? Sure it is. Are these equal? No. And that's why you can't just flip one side. You have to flip both. Once you flip both of them, then you can solve for T2. You can multiply both sides by V2. And what you have then is T2 is equal to V2 T1 over V1. And once you've got your formula, now you can plug and chug away. So V2 is 1.50 liters. T1 is 473.15 Kelvin divided by 5 liters. And you get 142 Kelvin. However, they asked for the temperature in degrees Celsius. Even though they asked for the answer in degrees Celsius, you still have to do Kelvin throughout because volume and temperature are directly related only for Kelvin temperature. How would you solve for degrees Celsius? Subtract, and you can just subtract 273. Keep it simple. And that is negative 131 degrees Celsius. Yep.
Are we going to be given these formulas on the quiz? Or?
I'm going to give you one formula that combines them all together, and I'll show you that one in about 10 minutes. All right? From the one formula, you have all of them there. So at this point now, Charles' law shows the direct relationship between volume and temperature. And we'll be exploring Charles' law in a little more detail in the lab next week. It's a cute little lab. I think you will enjoy it. Questions so far? So we've related pressure to volume, volume to temperature. What should we relate now? Temperature to pressure. The one missing piece. We're essentially just making a triangle from it. And so another gas law is known as Amintons law. Now in some textbooks they'll say Gay-Lussac's law. That one to me is a little bit different. So Amintons law shows again the direct relationship between pressure and Kelvin temperature when volume is held constant. If you increase temperature, gas pressure increases. This is why you don't put aerosol cans in the microwave. At very high temperatures, the pressure gets so great that it explodes. I don't know, this is an older movie, but did you see the movie Gremlins?
Yeah.
Remember they put the little gremlin in the microwave and the gases got so great that, poor little guy. So pressure and temperature are directly related. Same expansion that we talked about previously. Amintons law, P1 over T1 is equal to P2 over T2. Graphically, it's going to look the same as Charles' law, but your y-axis differs. And shown on the right here, if you have an aluminum can and you heat it, the gas molecules move around quickly, exerting pressure on the walls of the container, and the container essentially appears full. If you turn that heat off, you can see right here that the pressure decreases and essentially the container just implodes. Guess you could do that with a, you have to empty a soda can and then plug it in some way. But it'd be kind of cool. Maybe you don't even have to plug it. I think if you plugged it, it might explode. I don't know. We'll get in trouble for that. Alrighty. Let's take a look. We'll do the first one together and then you'll try the second one. It says a gas exerts 105 kPa of pressure on the walls of a 5-liter container. So we've got P1. They're giving us a volume here and a temperature of 30 degrees Celsius. The temperature is increased to 50 and we want to know the pressure. So they only mention volume once. Does the volume change? No. So the volume is constant. You don't need to include it in your calculation. So let's get the information here, and I need you to walk me through to make sure you're understanding. What does 105 kPa represent? P1. And what does 30 degrees Celsius represent? Do we want to write 30 degrees Celsius? No, we just want to be in Kelvin. So how do we do that?
At 273.1.
Good. And again, not degrees Kelvin, just Kelvin. Now the temperature is increased to 50 degrees Celsius, or 323.15 Kelvin, and we want to know the pressure. Does the temperature increase or decrease?
Increase.
What would you expect the pressure to do? Increase as well. Try and solve that one. What'd you get? What'd you get? What'd you get? What'd you get?
112.
Me too. KPA, right? You're not forgetting units, right? Otherwise, I'm going to go -1.
What is that? Kilometer Pascal?
Kilopascals. Yes, yes, easy peasy.
Yes.
Alrighty. Let's try. I think you're ready to fly solo a little bit, so let's try number 2. You do number 2. Go, go, go. How we doing? Be careful because you're solving for temperature. If you get a wee-wee answer, you probably solve for the reciprocal by mistake. you get what I got? Yes, yes? All right, and on these you really need to show your work. I don't need to see how you got Kelvin, but I need to see your work here. Please don't just plug numbers in. You're using quantities in chemistry. Once you get the temperature in Kelvin, you'll subtract 273 from it. So Amundsen's law shows the direct relationship between pressure and temperature. And again, in this gas chapter, you will always, always, always express temperature in Kelvin, or you will crash and burn. Kelvin, Kelvin, Kelvin.
So you have to start like with Kelvin, but you could end it with Celsius.
Yes. You have to do the calculation in Kelvin, but if they ask for Celsius, just subtract 273 at the end. Absolutely. All right. So we've got 3 gas laws so far, and we are going to combine them in what's known as a combined gas law, and that way the only formula you have to know is the combined gas law, although you do want to know that Boyle's law shows the inverse relationship between pressure and volume, Charles' law, the direct relationship between volume and temperature, and Amundsen's law, the direct relationship between pressure and temperature. Questions to this point? Okay. So we are going to derive what's known as a combined gas law. We have Boyle's law, we have Charles' law, and we have Amundsen's law. And we can generate one combined gas law where we have P1 times V1 over T1 is equal to P2 V2 over T2. And this is known as the combined gas law. You can see the inverse relationship between pressure and volume if temperature is held constant. You can see the direct relationship between volume and temperature if pressure is held constant. You can see the direct relationship between pressure and temperature if volume is held constant. So if you know the combined gas law, you have all the gas laws in one. Now this is a little harder to interpret because you're going to be altering 2 and looking at the effect on the third. So this is a little harder to predict. This is easy. If pressure increases, volume decreases. If temperature increases, volume increases. This is a little more involved. And we're going to walk through the first problem together, and then we'll see if you can do the second one. And if you can, then we will do a whole bunch of practice problems, and you will be in good shape for your quiz next week. And I'm reserving that practice day for you. All right, in the first example here, and essentially everything I just derived is shown right here, the combined gas law. In your example, it says 5 liters of helium exerts 99 kPa of pressure at 30 degrees Celsius. If the temperature and volume of the gas are increased to 70 degrees Celsius and 8 liters, here's the second set, we want to know the pressure that the gas exerts, and I'm also asking for a conversion here. So there's a lot going on there. Let's get the information down and see if we can process it. So first set of conditions, V1 is 5 liters. P1 is 99 kPa. T1 is 303.15 Kelvin. T2 is 343.15 Kelvin. V2 is 8 liters. And P2 I'm looking for first in kPa, which is what will pop out, and then in atmospheres, where we can do a simple conversion. My combined gas law formula is P1 V1 over T1 is equal to P2 V2 over T2. And I want to solve for P2. And again, you guys are all extremely strong in math, so the variable manipulation should be easy for you. T2's going here. Where does V2 go? You got it. Once you have your formula, you can just plug and chug. You've got P2 is equal to T2 P1 V1, that's a 5, over V2, bless you, T1. And again, if you use units, you'll see appropriate cancellation left in a unit of kPa, which is a unit of pressure. Also, what I do want to mention, some of you are having calculation errors on your assessments. The only parentheses you need are the ones in red. I put the other ones down because it's easier to read. Otherwise, sometimes it's just too schmeary. 343.15 times 99 times 5 equals, divided by open parentheses, 8 times 303.15 close. And I've got P2 equal to 70.0 kPa. And the other thing they did ask us to do was convert to atmospheres. And we talked about this the other day. I'm going to flip screens for a sec. We can go kPa to pascals and pascals to atmospheres. So what we've got here is 1 kPa is 1,000 or 10 to the third pascals. And we've got 1 atmosphere is 760 millimeters of mercury. Why did I put 760 mercury in there? That doesn't belong, silly. What belongs there? 101,325 pascals. And again, looking at unit cancellation, you'd catch it if you did something silly like that. And we've got 0.691 atmospheres. And again, it's okay to make a boo-boo, because if you go to cancel your units, you'll catch it, and then you won't make a boo-boo. Questions there? All right, you try number 2. Let's make sure you've got it. I'll pull it up on the screen in case you don't have your notes. Here's number 2. Give it a shot. How we doing? How we doing? Are you ready? Are you ready? She's going to pop on the announcement soon. I'll just show the answer.
Good afternoon, Cobras. Teachers, if you have not done so already, if you received blue and red testing cards, please at this time pass them out to the students that they were given to. Teachers also at this time, please turn on your computers and prepare for this afternoon's video announcement. Vista Venom strikes now.
So here's your answer. We will do our classwork on Monday, So if you are going to be out on Monday, you will want to pick up your classwork, or if you don't feel good about what we did today and want to jump start, I can give it to you today. These problems will go with the classwork. Your quiz next week will cover the gas laws we just did, same type of problems, as well as a little bit of nuclear chem, writing nuclear equations, neutron to proton ratio, and a half-life problem. Very straightforward. Most of the quiz is gas laws. So with the combined gas law, you've got all those gas laws in one. It's much easier to remember. You want to be familiar with Boyle's law, Charles' law, Amintons law, and you want to be able to calculate. And with practice, you will be golden.